So we start to discuss this time locality of BV formalism, because in field theory locality is a crucial condition, and a lot of things becomes much deeper and useful when we apply BV formalism to local theories. In particular, one arrives at a concept of local BRST cohomology, means cohomology of BRST differentials in the space of local functionals, and this is exactly the physical, and precisely these cohomologies have physical properties. Okay, so what does it mean locality? We know that in field theory, we ask our Lagrangian density to be a function of fields, let's say phi I, their derivatives, and I use, if I remember correctly, I use Latin, etc. And all of them are taken in one and the same point, and there is only a finite number of derivatives. So more formally, local functional. Let's make it a bit more geometrical. So when we are talking about fields phi I of x, geometrically we think of them as sections of fiber bundle f over our space-time. So x is space-time, and fibers of f are, let's say, target space. So field configuration of fields it's a section sigma, which takes us from x to a fiber bundle, to a total space of a fiber bundle, and section means that its composition with a projection is an identical transformation of the base. So the picture is like this, right? So we have our f, we have our x. So projection, so there are fibers. These are points which are projected to a point, so these are fibers. So this is pi. And section is a map from x to f, so which means it's a submanifold like this, such that if we take, for instance, this is sigma. If we take a composition of sigma with pi, we get an identity. So section sends a point on the base space, on our space-time, to a point of the fiber, which projects to this very same point of space-time. And then what we call fields in phi I of x, these are like coefficients of sections. So strictly speaking, this is sigma star, pullback map determined by sigma, applied to coordinates phi I, which are coordinates, local coordinates on f split into xa and phi I. So we take local coordinates on x and pull them back to the total space to get a part of coordinate system, and then we complete them with phi I, which are coordinates on the fibers. And then, given a section, we can write it down in coordinates by acting with a pullback map on coordinates on the fibers. Okay, and then we can speak about functionals. So I'll have space here. So local functional on sections, space of sections of our bundle. So let's say f of sigma. So it's a map which takes a section and gives a number, right? Local functional is a functional which can be represented like this. It's an integral over x. So let's say dnx, and suppose we fix the volume form of a pullback of a certain L, where L is a function like this. So it depends, Lagrange density. So it depends on our not very good. Strictly speaking, to write this formula, I need to introduce already jets. So let's say let me not use this pullback thing. Let me just say that a local functional is a functional of the following form, which is dnx, then some function of L, then we have phi I of x, dA phi I of x. We just do it explicitly without using this pullback map. Further derivatives, phi I of x, etc. And there is only a finite number of derivatives, and all of them are taken in one and the same point. Then we say that this capital F is a local functional, and a local field theory, classical, is a field theory whose action is a local functional, or equivalently, its Lagrangian density is a function of fields and finite number of their derivatives taken at the same point. So you can't have dependence on infinite amount of derivatives, or you can't have dependence on values of fields in different points. Then we speak about non-local theories. At quantum level, we know that there appear non-local functionals, like generating functionals of green functions. They are non-local, of course, but still a lot of information can be captured at the level of local functional, for which we have a powerful technique to work with, because if we work really with an infinite dimensional space of all field configurations and of all possible functionals there, then it's technically very difficult. You need to specify everything, and that's what we can't usually do. So we need some technique to work with local functionals, because, as I promised, they're precisely the ones which are of interest in field theory, in usual field theory. Okay, and the technique to work with them is precisely these jet bundles, which we discussed in the case of mechanical systems, in, let's say, simplified version of the same story. So what is a formal definition? If we have a bundle F over X, we keep same notations, so XA and phi I for coordinates. You can always think that this is just a space with coordinate X and phi, but coordinates, but they play different roles. So X are coordinates on space-time, and phi are like fields. These are coordinates on fibers of our bundle. Then, by definition, jet bundle of order k of f is as a set is just a collection of pairs p and sigma kp. So these are such pairs where p is a point of the base, so it's just a space-time point, and the second element is a point of the fiber over p, and this is an equivalence class of sections. But equivalence class, so let me write it. Sigma is section, so it's x to f. So what is the equivalence class? We say that sigma kp equivalence class of sigma equals to equivalence class of sigma prime. It means that all derivatives dl of sigma I of x over dx a1 dx al equals to same derivatives of sigma prime I dx a1 dx al. All this is evaluated at point P, and for all L less than equal to K. And here sigma I of x is just sigma star of phi I. So these are components of our, before I denoted it by phi I of x, but now let's better use notation sigma I to make sure that this is precisely coefficients of section sigma. Okay, so what does it mean? It means that a point in the fiber of our bundle, a fiber at P, is like equivalence class of sections such that these sections touches a tangent to each other to order k, which means that all their derivatives at this point, partial derivatives, up to order k coincide. It's easy to see what are coordinates on the fiber. So if we pick local coordinates on F, adapted local coordinates, where we have a split into like fiber coordinates and base space coordinates. So fiber coordinates, of course, is not a very invariant notion. You can always adjust them by change them in an x-dependent way. But suppose we picked certain coordinate system x and phi, and then we see that this equivalence class is just parameterized by values of these derivatives. So we can introduce coordinates. Let's call them phi I a1 al less than equal to k, and these are fiber coordinates of JKF, right? In particular, for instance, it's easy to see that if we take just J naught of F, this is precisely our bundle, right? Because what does this equivalence tell us in this case? That we don't care about derivatives, just values of sigma should coincide. Values of sigma should coincide, but value of sigma is precisely the point in the fiber. So our jet space in this case is a collection of pairs where P is a point on the base, and this is just a point of the fiber. So this is by definition our fiber bundle. one can show that this space is again a smooth manifold. Everything is good with it. We just introduce coordinates and we don't get into the mathematical subtleties because it's not our aim. So either you have a look in books or you believe me that the construction is okay from this perspective. Okay, very good. Then we have a canonical projection. So so if we have j k plus p, for instance, there is a projection to jk. It acts in a very simple way. So let's say this is pi k plus p k. So pi k plus p k acts on equivalence class sigma k plus p at point O. No, let me use another. Oh, I just denote by x the point. It's fine. X giving by definition same section, but understood as a representative of the equivalence class K, right? So it's a canonical construction. So remember, points of our jet bundle are equivalence classes. Pairs, of course, you have a point of the base, and then you have a point of the fiber. And point of the fiber is an equivalence class. So we take exactly the same section and just consider it as a representative of a different equivalence relation, which is more here, so to make sense, which is more coarse-grained, right? Which is more rough. Because if we take an equivalence relation where we ask all derivatives to order k plus p to coincide, here we only ask derivatives of order k to coincide. So there is this canonical projection, and we can write the following sequence, which never ends. So here we have jk, here we have j k. I skip this f, otherwise it's too heavy. It's clear that there is one underlying bundle, jk minus 1, etc. Finally, we hit j0, which is just f, and then there is a projection to x, right? So there is such a chain of projections, and it's a useful object is to define an infinite jet bundle. The idea is very simple, because if we want to consider functionals depending on derivatives up to certain order, sometimes it's not very useful to fix this order, right? Because maybe for some reasons you need to consider higher. So somehow the idea is to say the order is sufficiently high, and then you just set it to infinity. So take k to infinity, and this is called infinite jet bundle. Infinite jet bundle. It's already infinite dimensional space. And strictly speaking, if you want to define it mathematically correct, in a mathematically correct way, you take what's called projective limit. It means that looking at this picture, you are saying that the point of this projective limit is just a collection of points of j's of all orders, such that projection take and this collection is compatible with projection. So a point in JK projects to the respective point of JK minus 1. In this way, you can think of it in a quite an explicit way. So this is called projective limit, and this is infinite jet bundle, which at first glance look like an infinite dimensional space. And you can ask me, why do we actually do it? Does it help? In fact, it helps, because an important point is that there is a concept of local function. Not functional, though they are closely related. Local function, which is just a function on J infinity f of the form I infinity k star of f, where f is from C infinity of JK f. So it's, what does it mean? It means that this function f originates from finite jets. So it means that it only depends on finite number of coordinates up to derivatives of certain order. That's just a careful way to say it. So in some sense, these local functions, they are functions of finite number of coordinates. They behave pretty much like functions on finite dimensional spaces, and it's easy to work with them. In a similar way, one can consider local forms. For instance, this Lagrangian function is precisely an example of local function, because we require it to depend on finite number of derivatives only. In a similar way, we can define local differential forms. Because pullback is perfectly defined on in a similar way. Pullback is defined for differential forms, so everything works in the same way. In particular, what we will need are the so-called horizontal. Local. It's useful to have them. Local differential forms. Let's denote them by 0. So this is the degree of differential form, horizontal degree, and the vertical degree is 0. In fact, one can show, we don't need this, but in principle, one can introduce vertical and horizontal forms and the mixed. So this explains why the notation is like this. So there is like a b degree, and the vertical degree is 0, and horizontal degree is generic. Then we talk about horizontal differential forms, and these are forms of the in coordinates. They look like this. It's dx a1, dx al, for instance, and we have alpha a1 al, and these guys are already local functions. So these are differential forms which only contain differentials of the base space coordinates. Invariantly, horizontal differential forms are those which vanish if we evaluate alpha on V, it equals to 0 for any vertical vector V. Vertical means tangent to the fibers. It doesn't have components along the base, so it doesn't contain d over dx. That's why this holds. Okay, for instance, of special importance are horizontal top forms. If space-time dimension is n, then they are like this. So it's forms where you have top form here, and of course they're important because they eventually give integration objects on space-time, right? Now we can rephrase our definition of local functional. Moment, we need one more ingredient, sorry. So these are horizontal top forms. So these are the guys which has a number of the axes which equals the dimension of our space-time manifold. Okay, then we need one more ingredient, and then we rephrase our local functionals. So another ingredient is total derivatives. Total derivatives. They look like this in standard coordinates because we introduced coordinate system. So total derivatives are defined like this. It is Is everything fine? Can you hear me? Because I see some. No, I see that you can hear me actually. Okay, good. Do dxa plus phi I a do d phi I plus phi I a b do d phi I and b, etc. The pattern is clear, and in general, this dA, well, not in general, it contains infinite number of terms, right? Because it goes on infinite jets, it goes higher and higher in derivatives. But when we act on the local functions, then this expression contains only finite number of terms, number of non-vanishing terms, right? Because f depends only on derivative of finite order. So at certain step, you see each next term here takes the derivative with respect to like next level coordinates, which corresponds to higher derivatives. And hence, at some stage, you hit zero. So only finite number of terms are non-vanishing in this expression. And simple exercise, it's not really for it's not really for exam. It's to check that dB equals zero, so they commute. In particular, they determine involutive distribution, which is called Cartan distribution in this part of geometry. Okay, and now we also have another important concept, which is prolongation. If we have a section sigma x to f section, then we have its prolongation. It's canonically defined. Sigma bar, which is, in fact, it is defined for finite jets and also for infinite, doesn't matter. It's defined for generality for finite, jk of f, and it is defined by a very simple rule. So sigma bar, its value at a point p of the base, because section takes us from, it's a map from base space to fiber over this, to the total space, but more precisely to a fiber of this over this point. So the value of sigma bar at P is nothing but an equivalence class of sigma at this point, and K is of course the same, because by definition points of the fiber over P is an equivalence class like this. So there is a canonical to a given section, there is a canonically associated point of a fiber over each point of the space-time, and this this associated point is just an equivalence class of our section at this point. So in particular, let me also phrase it as an exercise, so it's, let's say, simple exercise, just to make sure we understand what's going on. If we compute sigma of bars with star pullback of a coordinate function, which is, for instance, phi ia, we are going to get nothing but d over dxa of sigma star of phi I, right? So in this sense, these coordinates phi ia can be regarded as derivatives of phi, though they are just independent coordinates, but when we evaluate them on prolonged sections, we see that they really become derivatives. So this is quite an important point to understand, that although if we just leave on our jet space all these coordinates phi I, a1, whatever, they are just independent coordinates on the fibers, on the fiber of our jet bundle. But when we take a pullback by prolonged section of such a guy, let's be more precise, A1AL, we get, of course, d over dx A1, d over dx AL of our sigma I of phi, right? Sorry, sigma star of phi I. Okay, and more generally, one can phrase it as a proposition, is that f local function then if we evaluate sigma prolonged star on dA on total derivative, what we get here is just d over dxa of sigma bar star of f. So you see, if we this also explains the name why this is total derivative, because if we evaluate it on a concrete field configuration, which means on a concrete section sigma, it becomes a real total derivative. But of course, this total derivative in the sense of jet bundle is just a locally defined vector field, first order differential operator, which is given by this expression. Okay, and now we are actually can give a nice definition of local functional. So f, let's say, which takes 6 sections of f to numbers, let's say real for definiteness. I ignore that our base space can be non-compact and integral might diverge. So let's say we restrict either to compact spaces or to sections such that this doesn't happen. So is called local. if it can be represented as f in the integral of x sigma bar star of L for some local form L in wedge n0 JFF. So it's a horizontal top form of degree and its dimension x. So we have a n form on our jet space. It's a local form, so it depends only on a finite number of coordinates. Then we pull it back by our section sigma, and this gives us the value of our functional on this section, right? So our functional takes sections and gives numbers. So the functional which can be represented as a pullback of a local form is called local functional. It's clear that these local functionals are determined by local forms. But if we are again on compact space, or our boundary conditions at infinity are such that all our fields vanish at infinity, then we know that in this integral, total derivatives do not play a role, right? So it means that if we introduce, to phrase it, we introduce horizontal differential, let's call it dh, well, or just capital D, that's good, which is dxa dA. So it's precisely like the RAM differential, but where the derivative is replaced with total derivative. And now it acts on horizontal forms because it brings dependence on dx, but it doesn't bring vertical differentials of fiber coordinates. So this is really, so D is a map from, let's say, k of k0 of our jets to wedge k plus 1, 0 of our jets. So it rises by 1 the horizontal degree. And then, of course, if we can neglect boundary contributions, then we have the following simple statement, that integral over x of sigma bar star of d acting, let me put nevertheless h as a notation, horizontal dh acting on lambda is 0, just because it's a total derivative, right? Let's check it. We know that, let's compute it. It's an integral over x sigma bar star. Here we have dxa dA acting on lambda, right? But we know that dA, when it goes through sigma star, becomes a real derivative. So this is nothing but just the RAM differential acting on sigma bar star on lambda, right? Because dx is not affected by sigma, because sigma doesn't act on x. So here we get just the RAM differential, so we only get a boundary term, so it is 0 under our condition. So what it means? It means that two different local functions might give the same local functional if they differ by a total derivative, or which is dh exact term. So that's why sometimes we can replace, using this gent bundle approach, we can replace a real in the sense of in the functional sense, right? Local functionals with like their symbols in a way, and so let's say symbols of local functionals. This is nothing but quotient space of top forms, local forms, so local horizontal forms, by the image of DH, right? Or if you want, if we fix a coordinate system on our base space, we can avoid working with differential forms. We can just say that our integrand L, just a local function, it gives a local functional, but the quotient, but the equivalence relation is like this. L is equivalent to L plus dA JA, right? This is the same, of course, as dx volume form. Let me denote it like this. dxL is equivalent to dxL plus dH acting on something, which is just J dualized to a differential form. Okay, so in other words, this space is very important, and this is a space of local functionals, or strictly speaking, symbols of local functions. But if you work in terms of jet spaces, you prefer, and if you make sure that you can disregard boundary contributions, it's a good idea to work in terms of this quotient space instead of real local functions, because it's much simpler to work with this quotient space of local functions, because you are almost working with something which is almost finite dimensional, right? And this is a space, for instance, where Lagrangian sits, right? Because if we are in the setup where we can disregard boundary terms, we identify Lagrangians which differ by a total derivative. So effectively, it means that our Lagrangian is an equivalence class of Lagrangian density. It's an equivalence class of Lagrangians modulo total derivative, or in terms of differential forms, the equivalence is like this: modulo total horizontal differential, right? Modulo DH exact terms. So another way of saying this is that so what I suggest is to, because we are now living in this jet space, to forget about these symbols and just for short call them local functionals. But if we really need to write a functional, we need to think in terms of sections. But for many applications, it's enough just to consider this space, which is much easier to work with. Okay, good. So what we say, alternatively, we can say that these local functionals are cohomology group of DH in the space of local forms. This wedge 0 of our jet space, right? Because top horizontal form is automatically annihilated by DH, just because you have already enough of DXs, and they give 0. But image of DH is precisely what we quotient in this cohomology, right? So it's degree of this of the cohomology of DH in form degree n in the space of horizontal forms. Okay, so that's a, let's say, homological characterization of local functionals, which appears useful sometimes. Okay, good. Then with these preparations, we can move on, but let me state a useful proposition which we will need in what follows, is that locally in the geometrical sense, locally, so it's like it's some neighborhood of, in fact, locally on our space-time, cohomology of hi dh wedge 0 of our jets equals 0 for I less than this dimension. So it's empty. It's analog of Poincare lemma if you want. So let me put I and yeah, like this. So in all intermediate degrees, and this cohomology is empty locally. If our space-time is non-trivial, if we do not restrict to a neighborhood in our space-time, then the RAM cohomology get into this game, but we don't discuss this more general statement. And it's clear what cohomology is in degree 0. These are also constants. So H0 of TH, the same is of course just R, right? Because they're or constants are annihilated by dh, and they can't be represented as dh on something. So it's exactly like Poincare lemma, but the difference is that in top degree we have a very important cohomology space which are local functionals, and this statement is called algebraic for some strange reasons. Algebraic Poincare lemma. So the difference with just usual geometry is that you get a huge cohomology space in top horizontal form degree. Okay, now we can slowly move to BV on jet spaces. The generalization is straightforward. So it turns out that the BV construction can be done for local field theory in terms of these jet bundles, and then you can always, of course, evaluate your objects on sections to get a real functionals which you need. For instance, master action is a local functional, and the fact that it is local means that it is determined by a certain local form or equivalence class of local form. So you can do majority of operations living on this almost finite dimensional jet space, which simplifies things a lot. So it's useful to develop the formulation of BV on these jet spaces. So the first step is rather simple. So we ask for, let me first give definition, that vector field V on J of F is evolutionary. If V commutes with total derivatives, and V is vertical, which means that it kills space-time coordinates pulled back to the total space. Okay, these fields are very useful because indeed they correspond to certain transformations. That's why they called evolutionary. And it's easy to characterize them because from this condition that they commute with total derivatives, it follows that it's enough to know, let's say we introduce phi I, which is V acting on undifferentiated fields, which means derivative coordinates on fibers of zeros, jets. And then these are local functions, right? These vi are local functions. Then we know that v acting on phi I, for instance, A1, AL, is nothing but v acting on dA1, dAL phi I, right? Because our total derivatives act precisely like this in standard coordinates. But because v commutes with dA, this is precisely dA1, dAL acting on vi, right? So it means that to characterize our vector field, it's enough to give these functions. It's enough to know how it acts on undifferentiated fields. The rest follows from the fact that our field is evolutionary because it acts trivially on space-time coordinates, and then we know how to act on higher derivatives of our fields. So this is a very useful object. So BRST and with this definition, we can say that BRST differential. I begin not with master action, but with BRST differential because it is useful. BRST differential is evolutionary vector field S such that S is nilpotent. So if you go twice on any local functions, it gives 0. So it's the same as before. But that's it. That's actually the only additional condition. And the degree, nothing changes with degree. So ghost number is also induced on our jet space just because it is built out of fields, and of course derivatives of a field have the same ghost number as the field itself. So ghost of S is 1. So it's a vertical field. It commutes with total derivative. It has degree 1. So you see already there is a difference with naive BV. It's not just a generic vector field. It's an evolutionary vector field, which is a very, very strong condition. So in particular, we can discuss BRST cohomology. BRST cohomology. S perfectly acts on local functions, so we consider H of S, and here we can take just, if you want, even horizontal forms, but let's say 0, 0 of our jets, which have just local functions. This is BRST cohomology, right? But it turns out that this naive BRST cohomology, which are analogous somehow to the ones which we had when we considered toy models, they are not really physically important. Because as I mentioned before, the really important ones are local BRST cohomology. So these are not, well, they're still useful, but these are not of direct interest. They appear in computations, but physical quantities like, for instance, vertices, symmetries, conservation laws, they are described by local BRST cohomology, not of just BRST cohomology. And what are local BRST cohomology? Formal definition is like this. So S acts, so we introduce equivalence classes of local functions. So we say that equivalence class of F is determined by the following equivalence relation. F is equivalent to F plus total derivative, where JA are some local functions again. And then we see that S can be defined as acting on these equivalence classes, just like this, SF. And this is well defined. I abuse notations a little bit because I use the same letter S to denote differential acting on local functionals, right? These equivalence classes, they are like local functionals. Now I don't use language of differential forms for simplicity. Just to give an idea, I suppose that there is a fixed coordinate system on our space-time, which is usually the case if we are in Minkowski, for instance. And then we can talk of local functionals as such in equivalence classes, right? And then S acts on an equivalence class by definition like this. So what we need to check? We need to check that it is well defined. S is well defined. How do we do it? It's very simple, right? We see what's going on. We pick another representative, right? Apply this rule, we get SF plus, but S commutes with dA. So here we get dA as JA, right? And this is the same equivalence class, SF. So it's well defined. So in other words, our space of local functionals, so this quotient space, is also a homological complex, and its cohomology is local BRST cohomology. So this is HI, cohomology group of S in space of local functionals. Local functionals. If we use language of differential forms, then we can say that it's H I of S in like this, right? What is let's do it more explicitly, because this is a very important homological group. So we see that S acts, S is well defined in equivalence classes, so we get a complex, and its cohomology is precisely local BRST cohomology. But let us write down it more explicitly. So I want to define it explicitly. So what does it mean in terms of representatives? So cocycles, it means that S acting on F is 0, right? Which can be rewritten in terms of representative like this. SF equals to dAJA for some J. And coboundaries, it means that F is equal to S acting on G, right? What does it mean? In terms of representatives, it means that F equals to S acting on G plus, again, dA on something, right? So this gives us explicit definition in terms of representatives of our cohomology group. This is called a relative cohomology. So our S, so cocycle condition means that our cocycles are elements such that S gives on them not zero, but total derivative, while elements which I consider trivial, which are S-exact or co-boundaries, are not just elements of the form S on something, but S on something plus, again, total derivative. If we take a quotient relation we mod out by total derivatives, we get the usual definition. This one, right? This is just a definition of usual cohomology. So cocycles, co-boundaries, the quotient space is cohomology. And in terms of differential forms, now let's assume that f is actually, well, let's use different, not to confuse, alpha is dxn times f. So we switch to differential forms. But of course, the language of differential forms is preferable because we don't need to think about coordinates on space-time and explicitly separate the volume form, and we can directly integrate these objects. So alpha has this form, so it's an element of top horizontal form of on our jet space, and we say that S acting on alpha should be what? Should be total derivative, which in terms of differential forms means that it is dH acting on some beta. And so that's what let me do it like this. So that's how this is translated. And let's translate also this. It tells us that alpha is equal to S acting on some bit, well, S acting on some gamma plus DH acting on something else, delta, for instance, right? So this is cocycle condition, this is coboundary condition. So the quotient space of elements satisfying this, modular elements satisfying this, is our local cohomology, local BRST cohomology. What is important to check, this is very simple, that if we have alpha of this structure, so if it's a coboundary, then it's automatically cocycle. Of course, it's a trivial cocycle. How do we check it? We need to check that S acting on alpha is dH on something. So let's substitute S acting on alpha is S acting on S gamma plus dH delta, right? S squares to 0, so the first term is gone, but S anti-commutes with dH because S commutes with total derivative, but dx is also an anti-commuting object, so it should be considered as a fermion. So it means that we have 0 plus minus, strictly speaking, minus dH S delta, and we have dH S delta with minus. So this condition is satisfied. So this trivial alpha is automatically a cocycle. So it says everything is well defined, and we have a definition of local BRST cohomology in terms of horizontal forms. Okay, then there is a useful characterization, another characterization of this cohomology, total BRST complex. It's technically usually a way to compute this local BRST cohomology, because you see, although it's very simple, it's very easy to define this local BRST cohomology, just a minor modification that all equalities hold modular total derivatives. Realistically, once you want to compute something, it becomes extremely difficult, because everything you always need to look for different representatives to everything is defined up to total derivative. It's a very very sophisticated object. Although people succeeded in computing this cohomology for variety of local gauge theories, it was a lot of work, and this work is really needed because, as I told you, this cohomology controls many physical properties of these theories. But it's quite difficult to compute them directly. That's why one of the first steps towards realistic computation is to pass to local BRST complex. What is this? The idea is to consider the following complex. So it's horizontal forms on our jets on which we get a differential S twiddle, which is dh plus s. And the degree is also tricky. The degree is, let's say, total Gauss degree is Gauss degree plus form degree. Form degree is what we have here, right? Because we are talking about we are speaking about horizontal forms, so this space is graded by horizontal form degree. Roughly speaking, the number of these dx's. So we have this new complex, and indeed we need to consider another degree because s rises Gauss degree by 1, but horizontal differential adds 1 dx. So it rises the form degree by 1. So it doesn't look like a homogeneous differential unless we pick a total degree, right? So this is total BRST complex. And the proposition which we have about this complex, that H, we can consider cohomology of S twiddle here in degree n plus I, and this is going to be isomorphic to local BRST cohomology Hi of S in functions, or let's say top forms. I haven't introduced notation, local functionals. Let's say local functionals, this usual local BRST cohomology for I greater than equal than 0. So you see what happens. Now we have a new complex, which is just a little bit more difficult because it contains extra variables, which are space-time differentials, dx's, and additional term in the differential, but it's just a usual cohomology. And this cohomology, at least in certain Gauss degrees, are isomorphic to cohomology of to local BRST cohomology, which is difficult to compute. Of course, it does not solve the problem immediately, but it's a first step of simplifying the problem of computing local BRST cohomology. And from this perspective, from this BV formalism perspective, at least, of course, BV formalism is a big thing, but what we discuss now, majority of issues amount to computing, to amount to knowledge of these local BRST cohomologies. That's why it's very important to compute them. I hope I'll be able to give a small illustration. Okay, and the idea of the proof is as follows. So let's consider generic element. So let's consider a cycle condition S twiddle acting on F. And let's expand. So this is our cycle condition. Let's expand F in terms of degree. So F is something like, so you see we have Gauss degree starting from at least 0. So it means that any F should start with form degree n element and I plus f n minus 1 I plus 1, etc. Right? So I use subscript to indicate form degree and superscript to indicate cost number. Okay, so I decompose f in two homogeneous differential forms. Because I have only total degree, my generic f contains horizontal forms of different degree. But the sum of Gauss degree and form degree should be constant, right? Because it's a total degree of my element. Suppose I'm interested in degree n plus I. So that's what it looks like. So let's consider what it amounts to, this condition. So it gives me S acting on F I n plus DH acting on F n minus 1 I plus 1, 0. And here, guys, but what is this? This is precisely the condition that Fni is a representative of local BRST cohomology. Again, let's now assume that F is trivial, so it means that F is S-Twiddle acting on G. Again, expanding in degree, it means that F and I is equal to S acting on G I minus 1 n plus dh acting on G n minus 1 I. It means that if f is a trivial, homologically trivial element, so it's in the image of a twiddle, it is the same as we saw before, right? That f, look here, is S acting on G plus total derivative, or more precisely this, because now we use language of horizontal forms. S on something plus DH on something. That's exactly what we recover here, right? Okay, so indeed, we see that this condition implies that F is that the first term, Fn, is a representative of local BRST cohomology, and if F is trivial, so it has the form as twiddle acting on something, then this F degree and form degree n term is again trivial. So it is consistent, but it's not yet a proof, and the proof is an exercise to show that essentially to show this isomorphism. Practically, it means that all higher terms or lower form degree terms are determined by this, and for this you crucially need algebraic Poincare lemma, otherwise it doesn't hold. This exercise is a proof of is a very standard proof in homological algebra. So I highly advise you to take an effort and try to prove this isomorphism. So I showed you that it might work. It looks very natural, but in fact it works provided algebraic Poincare lemma holds. So if our DH doesn't have cohomology in non-vanishing form degree. Oh, sorry, in form degree which is not top form degree. Exercise complete the proof. Okay. What can we do? Why I promised you an example of how this local BRST cohomology might work. What can they tell us about gauge theory? But to give such an example, I also need to understand how BV antibracket can be incorporated. Antibracket can be incorporated in the jet space framework. Naively, it just doesn't work because you don't have symplectic structure on jet space. So of course in BV we have phi I and phi star I, but this gives me symplectic structure only on fibers of my bundle. But if I go to jet bundle of, let's say, BV bundle, so for us now F is we have base space coordinates, we have fields phi I, and we have anti-fields phi star I. So these are coordinates on our F now, but we don't have bracket structure which involves derivatives, right? And also we want perhaps our anti-bracket, we want it to be well defined for local functionals. So what we do, we can do it. We can define anti-bracket on equivalence classes of local functions by the following rule. And this rule, because now we are talking about equivalence classes, is not unique. So so for equivalence classes it is unique, but for representatives it's not unique. So for instance, we can define it like this. We can define it as an equivalence class of Euler-Lagrange derivative of f d phi I, d Euler-Lagrange g over d phi star I minus other way around, like this, and then taking equivalence class. This way the definition is good because it has same symmetry, and also because Euler-Lagrange derivative annihilates total derivatives. It doesn't depend on representatives, so it is well defined. It is symmetric because symmetry is the same. But we can't speak about Leibniz rule because we can't multiply local functionals. That's a very important point, by the way, that local functionals you can't naturally multiply. But you have an anti-bracket on equivalence classes. But this anti-bracket is not very useful because first of all, you only have it on equivalence classes. By the way, exercise, check that this anti-bracket makes local functionals into differential graded Lie algebra. What does it mean? It just means graded Lie algebra, so there is a certain degree, and in fact it's not cos degree, you need to shift a little bit, plus a differential. Oh, sorry. It's we don't have yet BRST differential. We will add it when we have it. Just graded Lie algebra, because you remember, anti-bracket is has degree 1, but if we speak about graded Lie algebra, we want the degree of a Lie bracket of two elements to be a sum of degrees of elements. That's why you need to make a small. You need to make a small amendment to make the space into really graded Lie algebra according to its definition. And I remove differential because we don't have differential yet. Okay, but still, this definition of bracket is not very good because, in particular, it does not help us to produce BRST differential, because BRST differential is going to be, by our definition, BRST differential must be a evolutionary vector field, which is defined on local functions. But this bracket, as we defined it, is only defined on equivalence classes. So we can't find an evolutionary vector field. So the useful definition is different. And so we can define a bracket structure on local functions, which is not going to be a Poisson bracket, but still it's going to have some nice properties. And if it is still well defined on equivalence classes, and on these equivalence classes, it coincides with what we just defined. So we defined useful definition of bracket on local functions. Local functions. So what we do, we say that actually we define a Hamiltonian vector field. We say that bracket of H with G, where H and G are local functions, is VH acting on G, where VH is an evolutionary vector field. VH is an evolutionary vector field such that VH on phi star I equals to the Euler-Lagrange of H over d phi I, and VH on phi I equals to minus d Euler-Lagrange H over d phi star I. Or in other words, one can even, well, let's leave it as an exercise. So because it's evolutionary vector field, it's enough to know how it acts on undifferentiated fields. And here we give definition. So it acts just like, in fact, in the bracket above. That's why they coincide on equivalence classes, just by Euler-Lagrange derivative of this function h with a proper sign. But then we can extend it to anything. And a small exercise, write down general formula for Hg, which is equivalent to writing VH. So what we have with such a bracket? Such a bracket, by definition, satisfies, it is defined on local functions, not equivalence classes. It satisfies Leibniz rule for second argument, but not for first argument, because Euler-Lagrange derivative clearly is a higher differential operator, high order differential operator, so there is no chance for Leibniz rule. But we insisted on having this Leibniz rule for the second argument, and that's why we got what we got. And finally, this bracket coincides with the bracket above. So let's say here we defined alternative. So the end of exercise is to show that in fact f on equivalence classes fg alternative equals to equivalence class of fg usual. So it's same bracket if we go to equivalence classes, but it's very useful to have this bracket on local functions and such that it satisfies Leibniz rule at least in one argument. But of course, it doesn't have a proper symmetry property. It is graded antisymmetric, as anti-bracket should be, modulo total derivatives. So when we pass to equivalence classes, we do get symmetry relations. Okay, with this said, now what is master equation? Master equation. Of course, master equation, classical, means now that it should be satisfied by local functionals. So means by equivalence classes. It means that our SBV, let's better speak about not function, the Lagrangian equivalence classes of Lagrangians, LBV is now not zero, but it can be a total derivative. That's a very important point, that master equation is satisfied only for local functionals, for equivalence classes, which means that if we evaluate our bracket for representatives, if we picked particular representative Lagrangian of the Lagrangian, we don't get zero, we get total derivative in the right hand side. Of course, if we pass to equivalence classes, we get a usual master equation. But still, LBV with empty slot is a vector field, and this is evolutionary vector field because by definition our bracket is defined in such a way that for second if we leave second argument free, we get an evolutionary vector field, and S squared is zero on account thanks to master equation. Okay, and finally we see that our local functionals become differential graded Lie algebra. Now, in addition to the bracket, we have a differential S, which is well defined on equivalence classes, and we really get this differential graded Lie algebra. Okay, and may I have something like 5-10 minutes, because I want to give you one example, and then I want to stop. I want to stop at this point with, let's say, official part of the course. I still want to give one more lecture for completeness, with more details on local field theory and showing how this works, including Noether's theorem and things like this. But this is not going to be part of our exam, because I already exhausted the number of lectures which I'm supposed to give. So my proposal is as follows. Now I give one small thing, let's say 10 minutes. We stop official part with this, and then there will be one more lecture at some stage, maybe Friday, or we can agree if someone is interested. But this is not mandatory. This material is not going to be a part of exam, because I think it's already too late. Sorry about this. So what about this?
Okay, please explain us the example now.
Okay, so what I wanted to show is the general pattern of deformation theory in application to BV. So the setup in which this pattern appears is that suppose we have L Lagrangian, and suppose it is quadratic, which means that we have theory without interactions, and we want to ask a question, but it is gauge invariant. So in general, we completed to LBV, which satisfies LBV equal to, well, let me it's convenient not to write all the time. It's weakly 0, which means it's total derivative. So we have a linear gauge theory, and we want to ask a question: what are possible interactions in this theory? Because linear theory is not so interesting. It just gives us our physical spectrum, what are our one particle states, but we don't see interactions of our particles, right? So in order to see interactions, we look for nonlinear Lagrangians, right? Because vertices are precisely nonlinear. Nonlinear means cubic and higher. Quadratic is still linear because equations of motion determined by quadratic Lagrangian are linear. Okay, so what we are looking for? We are looking for deformations. So we are looking for, and let's call this guy even 0, 0, 0. What we are looking for is a deformation of our theory, which should look like this. It's L. Now, L is an expansion in homogeneity of fields for simplicity. So it's L0 BV plus L1 plus L2, etc. Where L2 is cubic, this is quartic, etc. And we want this equation satisfied to all orders. So if we found a non-trivial solution, we will see what non-trivial means. It means that we introduce certain interactions in our theory. And everything is consistent because the consistency is controlled by our master equation, which we impose. Of course, we also require that Gauss degree of L is 0, as it should be for the master action. But now we work in terms of Lagrangians, because we're in local field theory setup. Okay, so we expand this equation in homogeneity of fields, because our bracket takes homogeneity 2. So we get the following equations. We get that, of course, L0 BV, this we get in lowest homogeneity is 0. Well, this 0. This is automatic, and this is what we started with. And then we get a new equation, which is L, this 0 BV, with L1 is 0, right? And let me introduce a useful notation. So Q is going to be a free BRST differential. So it's a bracket with L not BV. So this equation is just QL1 is 0. So what we see that in L1, we precisely have a cycle of our free BRST differential Q. If we go to the next order in our perturbative expansion, what we have half L1 plus Q L2 weakly equals 0, right? And so on. All at generic order, we will have some kind of expression plus QLN is 0, and this does not involve Ln. It only involves L with lower values of indices. And of course, by the same reasoning as we had in many proofs, you can see that this expression which you have here is automatically Q closed. But this equation tells us that Ln this expression should be Q exact, so it should have a form of Q acting on something. For instance, here you can think of this as an equation on L2, or like on a completion of our deformation. what is important is the cohomology class of this guy. If we go with Q on L1, we get 0 because Q differentiates bracket and QL1 is 0. So we know that this is cocycle, but what this equation tells us that this is a coboundary. And on general ground, you can't show that this is a coboundary. So in principle, they can be an abstraction. So what is the message of what we understand now? That first order deformations in field theory terms, cubic vertices, are cocycles of our free differential Q. And then some first order deformations, in order for our first order deformations to complete to higher or to second order, we need this abstraction to be trivial, so that this guy is Q acting on something. So again, it is controlled by cohomology. It's a cohomology problem, whether this is a trivial cohomology class or not trivial or non-trivial cohomology class. For instance, if we know, simple example, if we can prove, suppose that H in degree 2, because this is element of Gauss degree 1. So suppose that H1 of our Q in local functions, local functionals, because now we are really talking about equivalence classes. H1 of Q in local functionals is 0, then any L1 is extendable. So it's not very interesting situation, but at least you know that some interaction exists, right? So at first order deformation L1, you pick take a cycle, and then you know that if cohomology, if you don't have cohomology in degree 1, but you do have cohomology, for instance, in degree 0, you can always extend. You can find such a consistent deformed theory. So you see the abstractions to deformation, they sit in cohomology in Gauss degree 1. And this is cohomology in the space of local functionals, because of course we are working with master equations and the student representatives, but here we have this equality sign, which means modulo total derivatives. So everything is modulo total derivatives. So we are in the space of, in the quotient space, in the space of local functionals. But in fact, it turns out that first order deformations are also classified by cohomology. So we see that first order deformations are necessarily cocycles. But suppose that first order deformation is a coboundary. So suppose that our L1 is actually, let's say, weakly. Yeah, I use this weakly equality. It's a good idea. Q on something. Q on, let's say, K1. What happens? Then it turns out that you can always complete such deformation, and this deformation is in a certain sense trivial. Indeed, let's consider the following object. Let's act with exponential of a bracket with K1 acting on our L not BV. What do we get? So K1, L1 is cubic, so K1 is also cubic because Q is linear, right? So there is it means that we can expand, if we expand exponential in Taylor series, it's going to be just an expansion in homogeneity degree in fields. So what it's going to look like, it's L naught BV plus K1 L naught BV plus half, sorry, where am I? Here, half K1 L not BV, etc. So this term is of homogeneity 2. This term, what's wrong? This term is of homogeneity 3. This term is of homogeneity 4. So it's just a homogeneity expansion. And you see that this, in homogeneity 3, this is precisely Q K1. So it's L1. So which means that if we take a trivial deformation, it amounts just to certain field redefinition, right? Because this exponential of a bracket with K1, it's an exponential of an evolutionary vector field, and it's nothing but a field redefinition. So if our first order deformation L1, if it is homologically trivial, so it has the following structure, then this first of all, it always completes to a full, to all orders. It's easy to write down in a closed form, the completion, but it also follows that this deformation is kind of fake one, right? Because it's still a quadratic action to which we applied the certain canonical transformation, which is exponential of such a vector field, right? So this deformation is called trivial, so trivial deformation. In other words, what we conclude is that first order non-trivial deformations is nothing but cohomology in degree 0 of our Q in local functions, let's say, of homogeneity degree 3. So we see a homological characterization of first order consistent deformations, and sometimes these guys are called cubic vertices. So if you consider just anti-field independent piece in this L1 is going to be a cubic expression in fields and their derivatives, which corresponds to certain vertex, certain interaction between our fields. And this is a technique where you can prove, for instance, that there are no deformations, or there are only deformations of this and that type, etc. So it gives a mathematical framework to analyze such an issue as existence of consistent interactions in gauge theories and things like this. It's still a difficult problem to compute explicitly this local BRST cohomology, but once you know it, in principle, you know consistent deformations, you know what are possible abstractions. In fact, same concerns, algebraically analogous technique, but with certain complications, lay behind the renormalization in terms of Zen-Justin equation, which we discussed last time, and many similar things like this. But the simplest one, the clearest one, is the story of consistent deformations of gauge theories, because it's purely of homological nature, and the relevant homological complex is the one of undeformed theory in the space where the differential is Q and the space is local functions, local functionals, the quotient space of local functions modulo total derivatives. That's the complex which controls these deformations of a free theory. Okay, very good. I think we have to stop. Unfortunately, I didn't reach something very explicit. It would require a few more lectures, and I'm afraid both of us, many of us, you and me, we do not have time and power for this, but I still wanted to give one more to show the last subject is the proof of locality of BV and what it looks like. Because for the moment, I just assumed that I have BV formulation of a local theory whose master action is a local functional. But what I want is to make sure that this exists. So if I start with a generic, of course, satisfying certain regularity assumptions, generic local gauge theory, I can build a BV formulation which is local, which gives me all these tools of local BRST cohomology to analyze it. So that's what I wanted to, I still want to give, because I believe it's an important, also important piece of the story. It's also closely related to Noether theorems, because they're an important part of these considerations. And that's what I want to give as an additional lecture. But let's agree, because it's too late already, that if you don't want, if you get, let's say, on exam, if you get a question related to this last lecture, you can refuse, because it's already end of semester, so I'm not allowed to give more official lectures. Okay, thank you very much.